guys, it's me, Marc, and in the last video, I was explaining the Standard Model, which is divided in two groups, the fermions and the bosons, and I spoke about the fermions. So today, I'm going to explain the bosons. Like I said earlier, bosons are force carriers or interactions that allow all the 12 fermion particles to interact with each other using four forces: a strong force or strong nuclear force, electromagnetic force, weak force or weak nuclear force, and gravity. Gravity is not included on this list. And also a particle or boson that gives other fermions their mass, the Higgs boson. Now I'm going to talk in detail about each and every particle and force. The strong force. The strong force, as the name suggests, is the strongest force. Gluons exert the strong force. Gluons are particles inside a proton or neutron that allow the up and down quarks to interact with each other. They are even responsible for forming a nucleus. Say, we have two protons and two neutrons trying to form a helium nucleus or helium ion, but the proton and proton, since both positively charged, repel each other. And the neutron and neutron don't interact or don't repel as they have zero electric charge. They are electrically neutral. But the gluons can overcome this force of repulsion between the protons, attract all the protons and neutrons, and form nucleus. Only quarks can interact with this force. Gluons sort of come from the word glue, which means, and they're called gluons because they stick things together. Photon or electromagnetic force. The electromagnetic force is the second strongest force. Photons exert this force. They have zero mass and can travel at the speed of light, which is denoted by c in a vacuum, and are represented by y, the Greek word gamma. The speed of light is 3 multiplied by 10 raised to the power of 8 meters per second. Photons are even responsible for magnetic attraction and repulsion on the quantum level. Magnetic attraction and repulsion on the quantum level is a bit different than in classical mechanics. For attraction, we've got to think of a skating park, but with no skateboards, rather with a circular object like a ball. Now, not only would the balls be attracting each other, they'd be attracting while decreasing their altitude with no influence of gravity. And for repulsion, we've got to think of a hill. Well, mine looks like a parabola. Now, not only would the balls on the hill be repelling each other, they'd be repelling while decreasing the altitude with no influence of gravity. Now, photons are called the quanta of light. Light is just an electromagnetic wave that bounces off the surface of objects, reflects into our eyes, registering that knowledge in our brain. Now, photons travel on this path that intersects the electric and magnetic field. These vertical waves are the electric field, and these horizontal waves are the magnetic field. Now, photons travel on this path that intersects both, or they sort of exert both electric and magnetic forces. They're called the quanta of light. Now, magnetism and electricity just both form a dual force, electromagnetism. Neutrinos, well, all fermions can interact with this photon, except neutrinos, or the electrically neutral neutrinos, because they have zero electric charge or are electrically neutral, even neutrons for that matter. A particle has to have a charge with a positive or negative to interact with the photon, and particles that don't have a charge will not. Weak force or weak nuclear force, the W and Z bosons both exert this force, and all particles can interact with this force. Now, the weak force in both particle and nuclear physics is responsible for the radioactive decay of atoms, and even for a phenomenon called beta decay. Beta decay is when a W or Z boson collides with a neutron in a nucleus, turning it into a proton with the emission of an electron and electron anti-neutrino. The Higgs boson. Now see, bosons are again divided in two groups, the gauge or vector bosons and scalar bosons. Gauge or vector bosons include the gluon, photon, W and Z. And scalar bosons, well, there's only one scalar boson, that is the Higgs. Now, the Higgs boson was described as the God particle by Nobel Prize-winning physicist Leon Lederman, as he tried to poke a joke at how very, very difficult it was to detect the particle. Now, the Higgs boson has been discovered, but there are still experiments at the LHC, which is the Large Hadron Collider, like ATLAS and CMA, trying to prove its existence. The Higgs gives particles their mass, and yes, is 100% related to the three generations of matter. Now we're going to take a top quark from the third generation and an electron from the first generation and compare the interactions with the Higgs boson or God particle. Now, as you see, our third generation top quark interacts far more times with the Higgs boson as compared to our first generation electron. But they don't really interact thrice or once or twice with the Higgs boson. The numbers on how many times they interact are yet uncertain. In conclusion, the Higgs doesn't interact with all particles the same way. The more it interacts, the more heavier particles get. Also, the more they slow down. The Higgs boson can also interact within itself, and in conclusion, slowing itself down. Now, protons, as we see, protons are heavier than neutrons, and the God particle is the only thing allowing them to stay like that. If the Higgs boson were to disappear, protons would spontaneously or even instantly decay into neutrons, and we'd have a universe without protons. Gravity. Now, as you see, gravity, nor the particles for gravity, is not included on this list because gravitons are said to exert this force, and they are hypothesized. They haven't been proved experimentally. That's why they aren't included. We don't know the properties of gravitons, like their mass, spin, and charge. Now, the interactions, which particles they'd interact with, how they would interact with, and yes, many questions are left unanswered. However, the standard model, according to some scientists, is yet incomplete because it doesn't have a particle for dark matter or dark energy. Dark energy accounts for 68% of our universe. Dark matter accounts for 27% of our universe. And yes, the remaining 5% is of all the matter we see around us. And to make things worse, dark energy and dark matter are both invisible. Nor does the standard model tell us how did particles come into existence, like at the Big Bang. Anyway, that was the end of my explanation of the standard model. If you liked the video, please hit the thumbs up below. If Feel free to comment and subscribe. Bye!